Professor Anton Zeilinger, welcome to Cambridge.
Hi.
Later on you're going to give a lecture on from Einstein to quantum computation, so looking forward to your lecture. And I'm going to ask you a few questions just around similar themes. Could you tell me what entanglement is? What does entanglement mean?
Well, entanglement is a notion which was discovered in the 1935 to be one of the really most mind-boggling consequences of quantum physics. Quantum physics or quantum theory at that time was about 10 years old. Modern quantum theory was created in 1925-26. And in 1935, Albert Einstein discovered that two particles which interacted in their past remain connected in a strange way, even if they are separated over large distances. And the Austrian physicist Erwin Schrödinger coined the notion entanglement. What it simply means is that a measurement on either of the two particles also changes the quantum state of the other one, no matter how far it is away. This is what Einstein didn't like. He called it spooky. And the interesting thing is that we now know that nature really works that way.
Mm. So I've heard of this notion called Bertelmann's socks. Mm-hmm. Could you tell us what that means, and could you tell us something about the difference between classical correlation and quantum entanglement?
Well, Bertelmann is actually a colleague of mine in Vienna. He used to work with John Bell, the very famous Irish physicist, who discovered what is called Bell's theorem. What Bertelmann does is, and he told me that he does this since he was about 17 or 18 years old. He started to do it as a kind of protest against the establishment. He carries always, until this day, he carries differently colored socks, like a white socks and a black sock. And the point is that if you know this, and if you see one of his socks say it's black, then you immediately know that the other sock is white. Which is trivial. I mean, it's obvious. There's nothing very interesting there. Now, if these were quantum socks, then we can actually prove through experiments that before you look at them, neither of them has a color. Neither of them knows whether it will turn out to be white or black. But if you observe one, if you do a measurement of the color of one, because looking at it is a measurement of color, if you do a measurement of color, then it will randomly assume white or black, and the other one will immediately turn into the opposite color. Mm. So in both cases we have what we call perfect correlation. If you know one, you know definitely what the other one is. But in quantum physics, we have no explanation in a common sense way, because these two socks don't know what their color will be. So how this correlation comes about is the big mystery.
So entanglement sounds strange, and it's surely a thing that's very interesting to investigate and research. But is it interesting for the modern world? Can it be used in any way? How could we make use of this?
Well, this is actually one of the most fascinating stories in my field. In the 70s, experiments started in different laboratories to show that entanglement really exists. And many experiments have confirmed now that nature is really that way. And these experiments were only motivated by philosophical curiosity. People wanted to know whether nature is really that way. And suddenly, in the 90s, early 90s, ideas came which suggested that entanglement might be for use. One of the first ideas was the idea of Professor Eckert here, who is now here in Cambridge, to use it for quantum cryptography. To use it to encode messages in a way which is much more secure than any other encoding. And today now, we have 2004, entanglement not only has been shown to work in these schemes, we are actually working on there's a large European project, we're actually working on building turnkey devices using entanglement in banks or whatever.
Some of my colleagues here at the quantum group have told me that there is some disparity between people working on the sort of theoretical aspects of entanglement and people actually working on the actual experiments, that some of these ideas that are theoretically being sought out could perhaps never been realized in practice. What do you think about that?
As an experimentalist, I would never use the word never. The point is that experimental progress is, number one, unpredictable, and it can be much faster than we all imagine. Some of these experiments we are doing today, I would never have believed like 10 years ago that we are able to do it. So I always tell my theoretical friends, don't let your fantasy be limited by what is possible today, because you might miss something important.
Now, I think entanglement can also be used for quantum teleportation. Can you tell us something about this notion of quantum teleportation?
Quantum teleportation is probably the most fancy thing you can do with entanglement. And the idea is simply to transform all information one system carries. We are talking about one particle of light or one atom. Transfer all the information one system carries over to another one, such that this other one becomes absolutely identical with the original. And it's not just a copy, it's not just like fax, because the original by necessity loses its original features. It's very strange. And this is again done using entanglement. Using entanglement, this strong connection to transfer all the information from A to B.
Could you tell me why Heisenberg's uncertainty principle isn't a problem for quantum teleportation?
That's a good point. Heisenberg's uncertainty principle tells us that we are never able to know all information characterizing a system unless we have already a lot of knowledge about it. There are small exceptions. Quantum teleportation is not an exception because we transfer the information, but we don't know it. Actually, teleportation only works if you don't get any knowledge of the information which you transfer. So this is really an elegant trick, which I would not have expected. I mean, this was the idea of 6 theoretical colleagues in 1993. Was a complete surprise.
And at least the transmission of the signal in quantum teleportation is instantaneous because it just works through entanglement.
Well, the way I like to say it is that the quantum information arrives instantaneously. So in other words, the particle over there knows instantaneously the information, but an observer cannot make use of it, because the information might arrive in 4 different ways, and the observer has to know which way this information transfer, which is an entangling procedure itself, actually worked. And for that information to arrive, for that knowledge to arrive, we are still limited by the speed of light. So there is no conflict with relativity, but it's actually really amazing how close it gets and just not violates relativity. It's really fascinating.
But this extra classical signal that needs to be sent, what information does that contain? Does it just tell you, in a sense, we now have teleported and you can take the result, or does it have to carry any additional information?
No, it says we have teleported this way, this way, this way, this way, 4 different ways. Okay? In all 4 cases you have succeeded, but it's 4 different ways, and therefore the system over there is in 4 different states, which the recipient has to look at in the right way to get the original information.
Okay. What do you think, notwithstanding your comments on never to limit your imagination earlier on,
right,
what do you think is the limit on objects that can be teleported in this way, in terms of size?
Well, in terms of what let's put it that way, starting from what we know today, what's experimentally possible, and extrapolating into the future, I'm sure that within my scientific lifetime, we will see quantum teleportation of the states of small molecules, maybe even larger molecules, but there's nothing which in principle limits things. I mean, but at some point, quantity turns into quality. So if things are so horrendously complicated, then you might still say that it will never be possible. So for sufficiently large objects where I cannot put any number, but we are talking about things of the, probably anything living. Teleportation is still fantasy. But you never know. I mean, maybe some young chap has a bright idea and off we go. You never know what might happen.
I'd like to ask you a few questions about the sort of philosophy behind quantum mechanics. You've already hinted at that quantum mechanics doesn't really violate the speed of light. It comes very close, but it doesn't actually violate causality, I should say, which is connected to the speed of light. So how is it that quantum mechanics knows about the speed of light?
I don't know. That's actually an interesting question. My friend Abner Shimoni, a physicist and philosopher in Boston, talks about peaceful coexistence between quantum theory and relativity theory. Why it is that way, I don't know. That's a very deep question, which I think is not really answered yet.
So there's also the Einstein-Podolsky-Rosen paper, which puts forward that quantum mechanics implies either the non-existence of objective reality or the non-existence of locality. Can you say something about that? And would you say that's still a valid interpretation?
The point is, there's not only a Bell theorem, there's another theorem which is called Kochen-Specker theorem. It's much less known. And that theorem tells us that the culprit is actually our notion of reality. Because the Kochen-Specker theorem talks about properties of one system only. So we know that we cannot assume, to put it precisely, we know that it is wrong to assume that the features of a system which we observe in a measurement exist prior to the measurement. Not always, I mean in certain cases. So in a sense, what we perceive as reality now depends on our earlier decision what to measure, which is a very, very deep message about the nature of reality and about our role in the universe. We are not just passive observers, like looking at the stage and watching things. We have a much more active role than in classical physics.
But couldn't one say that this involvement of the observer is really just limited to very small quantum mechanical systems, and once we come to the real world, surely all quantum effects would have just gone?
As people say that, and this is a comforting possibility, but there's no reason to believe that. Nothing in the theory tells us that. There's no limit for the validity of quantum mechanics. And we and other groups are actually exploring how far can you go. And I'm sure that we will go to sizes which will be quite surprising. So in my eyes, this is just temporary. In the future, we will realize quantum phenomena for sufficiently large objects such that it's obvious that quantum mechanics cannot be limited to small particles. And then the philosophical implications become more relevant because people cannot put them into some corner.
I mean, for instance, if one looks at interference, for instance, a double slit experiment at school, or a school beginning at university, one hears about photons and one hears about the same experiment being done with electrons. Can we do this with more complicated objects?
Well, in my group in Vienna, we did this with very large molecules of masses of 1,000 times the hydrogen atom. And our results imply that there will be no serious limits up to masses of 1 million or 10 million atomic mass numbers, which are masses of small viruses. So up to there, it is only an experimental challenge to find the right techniques to put these systems into a beam, measure them, and so on and so on. Beyond, I don't know, it would be too far to extrapolate, but again, I cannot see any fundamental limit.
So even going beyond very large masses, or do you think there is, because you said there's several million, there might be a cutoff?
No. I'm saying that our present experiments tell us that we can safely go to about 1 million.
Okay.
And I just wouldn't want to dare to extrapolate further. That is all. But there's no indication that this will be a limit.
I mean, if you think about a photon and a double slit experiment, I'm kind of prepared to think, okay, well, I don't know exactly which slit it went through, but it's just a photon. It's such an inherently quantum object that I don't mind so much. But if we're talking about a C60 atom, if we're talking about buckyballs going through double slits, one is really confronted with quantum mechanics in a sense, because it's almost, to a lot of intents and purposes, it is a macroscopic object, it's a big molecule, and in a sense we're saying, well, we don't know which slit it went through.
Yes, it's all about information. I mean, you get quantum interference when you have no information, and when nobody could have any information about which slit it went through. So, in a sense, this tells us that we should not talk about notions, about properties of systems which we don't actually observe. So the question whether the particle goes through one or the other slit only makes sense if I set up an experiment. If I don't set up that experiment, I cannot even consider it having it gone through one of the two slits, because that leads to a wrong prediction for the experimental results. But it is also wrong to say that it goes through both slits, because there is no evidence for it going through both slits. All we can say, there's no information present anywhere what it really did.
You've been attributed with wanting to drive a truck through an interferometer. Is that true? Have you already said that?
No, I never said that.
But would you say that it matches your ambitions?
I never said something like that, no.
Okay.
No, this is wrong.
Sure. Yeah, it's just something that I'd heard.
I mean, I simply said, something I said, and I can now understand what turns out. In some older textbooks, you read that we will never see quantum interferences of large objects like trucks, because their wavelength, the de Broglie wavelength, is so much smaller than the size of the object. And I keep saying that this is a bad way to argue, because for many objects, including these large molecules, we have that situation already, that their wavelength is much, much smaller than the size of the object. And I then say usually that this is not the reason that we will never see quantum interferences of trucks. There may be other reasons that we will not see them, but this is not the reason.
Okay, that's very interesting. Moving slightly on, could you briefly say what a qubit is?
Oh, this is difficult. This is like carrying coals to Newcastle. I mean, here in Cambridge, where people like Arthur Eckert are, the notion qubit was actually coined, I think, here. Was it in America? I don't know now. No, it was Ben Schumacher in the United States. Qubit is simply a two-state system with the states which I might call 0 and 1, like the two values of a bit, where the two states corresponding to 0 and 1 can be in a quantum superposition in the same way as you can have the molecule going through the two slits being in a superposition of going through the two slits.
And I've also heard of a Q-trid. So what's a Q-trid?
A Q-trid is then three-valued. A three-valued quantum system with three values, 0, 1, and 2, and you can go on. 4, 5.
So why would I want to do that? Why would I want to look at such systems?
Oh, basically because it's fun, it's interesting. I mean, it's obvious that you can pack more information into a Q-trid than into a qubit. So this might offer new ways of playing with quantum information. There are schemes, new quantum games, which explicitly use Q-trids and so on. So it's an interesting field. Whether it will be really useful, nobody knows today. This is certainly open.
mean, certainly the name qubit suggests that it's something that's going to be used in quantum computation.
Right.
Do you think that Q-trids or Q5s, Q7s might have special applications within quantum computation?
As I said, there are ideas suggesting special applications, and there are some first experiments already out. Whether this will be really useful is too early to tell. Nobody knows.
I mean, I was sort of thinking, could this be the end of binary computation? Could it be that other things come in and we suddenly have to rework our notions of sort of the fundamentals of computing?
Well, I think it's even much deeper. The whole field of quantum computation at present is still very much patterned after classical computation. Like having some information which you operate on sequentially using gates and so on, which is how a classical computer works. It is not really obvious to me that a quantum computer by necessity needs to work that way, because quantum physics is in a sense a holistic theory which kind of doesn't like to be separated into parts. And so I feel that there's a fair chance that our notion of computation might change.
Just to bring the interview to a close, I'd like to ask you some questions about yourself. How did you first get interested in studying physics, say at school or as a fresher at university?
Well, these are always difficult questions, because I learn from friends who work in oral history that people tend to put together stories about their life in which they believe themselves. Then, this is a difficult question. But I know that I was interested in scientific questions very early. I was always curious about things, and I was lucky to have a very, very good physics teacher in what we call gymnasium. I don't know how you call this in this country.
A-level.
When you are 17, 18. A really gifted teacher who was able to excite us.
So how did you get into your present field of expertise? When did you decide that quantum was for you and doing quantum experiments?
Well, actually very early. When I studied at the University of Vienna, there was basically no formal curriculum. You were very free to choose what you do. And interestingly, I did not go into a single quantum mechanics class during all my university education. So I learned it for the final exams. There were big exams, I had to learn it. So I learned it only from books. And from the first moment on, I read it, I was totally excited. So it might actually have been helpful that I learned it rather late. And not too early. I don't know, but this might actually be interesting,
And talking outside physics and outside quantum theory, which area of science do you find most interesting, most inspiring outside quantum mechanics, outside physics?
That's difficult to say, because essentially every question in science is interesting if you dig deep enough. They're fantastic. I mean, obviously, molecular biology is interesting, but it's not the only one. I mean, just today I flew from Vienna to London, and I was lucky enough to be in the cockpit. The pilot invited me to join them, and just to look at all these weather patterns is completely fascinating. You see waves and you see ripples and all kinds of things. I think basically in science everything is interesting.
And just as a brief roundup, why should somebody study physics today? For somebody choosing their A-level courses or choosing their university career, why should somebody study physics today?
I think it's a completely fascinating subject. And my basic opinion is that if you look at history, we do science only for a few hundred years. Physics, 300, 400 years roughly. So it's a very short time in the history of mankind. It is hard to believe that we found many of the essential points thus far. I'm convinced that there will be many surprises around the corner.
Professor Zeilinger, thank you very much for the interview, and I'm looking forward to your lecture.
Thank you very much.